right, guys, I'm really happy to be here. Actually, I want to thank Ent for allowing me back to talk again. So this is actually going to be an exciting time for me to talk because I feel like I've been up on stage for the last 7 years, hundreds of times a year, talking about, like, next year is the year for network virtualization, and I promise people are going to be using SDN soon, and I see the knee of the curve, and it's about to happen. And actually, this is actually one of my first talks ever where I get to say, well, it's happened. And so I've got kind of 2 points of this talk. The first one, well, I'll catch you guys up to speed on kind of provide the background if you guys don't have it. And then I want to be like, OK, so listen, we're here. People are using it. This is generating a lot of money. We've got evolving use cases, and talk about why people are using SDN and network virtualization and how they're using it. So you kind of get an intuitive feel, both technically and from a business standpoint. And then I want to kind of cast a look into the future again to see how this is now going to evolve going forward. So that's my talk. So let me just start with background to catch you guys back up. So I'm going to talk about network virtualization, which is one of the killer applications of SDN. And I want to give you kind of an intuition of when it came from. So let's just start with a traditional data center. In a traditional data center, I'm a networking guy, so I'm going to focus on the network. Networks in traditional data centers, I mean, they're normally some core technologies. Often they have proprietary technologies for good reason, because there are shortcomings in standard technologies. And this is where a lot of stuff that we need to do with IT is done, is in the network, in the hardware. Things like security or fault isolation or whatever it is. So if you go to any random enterprise today, and you look in the data center, and you look at the networking gear, it's probably vertically integrated. Chances are great that it came from one vendor. And a lot of the value of IT is implemented directly in that hardware. The upshot is you can run any applications on these things, your operators understand it, and this is how we've been building networks and data centers for the last 20 years. OK, so it turns out if you look at a modern SaaS data center, and I'm talking about the Googles and the Amazons and Facebooks and Azures and Tencents and Baidus, the picture is incredibly different. So instead of having, kind of a more complicated L2, L3, maybe a proprietary network, you generally just have a very basic IP network. It requires almost no configuration. And it has almost no manual intervention at all for anything. It's just an IP fabric that forwards packets. And functionality that has typically been there, right? I mean, you still need security. You still need fault isolation. You still need these services. But instead of actually having it being done on this hardware, it's now re-implemented as part of the application. Right? So if you take some random, like say some large search data center, you've got a very simple physical network. And then things like discovery, things like security are now part of either the operating system or the web server or the application. Okay, so this isn't just kind of something that's technically cool. The impact is profound. Let me try and describe it simply. So if you tie functionality into hardware, you have 2 problems. Well, CapEx is normally much larger just because of vertical integration. OpEx is much higher because you need people on a proprietary interface that are running around doing things. But innovation speeds are actually much slower as well. As you tie functionality to hardware, you fundamentally evolve it at hardware design cycles, which is what, 4 years? So if you compare, and the great thing is you don't have to, you don't have to trust me. You don't have to take this from first principles. You can actually look at these data centers. So if you look at a modern data center, these are the most efficient from a CapEx, OpEx standpoint. They evolve the fastest on a functionality standpoint. They support the most successful business on the face of the planet, and they're the most scalable data centers on the face of the planet. And what's great is we can just stand back and just compare the 2. So in these, if you move functionality away from hardware and you move it into software, well, now you don't have to configure anything. You can buy networking gear from your favorite provider, but the requirements are to pass IP packets. And now innovation is moving at software design cycles because we've taken these features and we've put them into software. So that's kind of the state of the world for the last 10 years. I mean, this has kind of evolved over the last 10 years. So the problem has been, unless you own the application, unless you're Google or unless you're application and or Amazon, and you're writing your application, you can't have a modern data center by this design. If you're an IT shop and you're deploying SAP and SharePoint and whatever it is, these haven't been written to take advantage of a data center like these. So even though it's clear what's the best architecture to build a data center, which is SDVC, it's very clear. I mean, we could go through hundreds of examples on the most cost-effective data centers on the planet. That's definitely the way to do it. But unfortunately, if you run IT, that you can't get those benefits because you would have to rewrite all your applications. So this is the background for network virtualization. What network virtualization says is, you know what? I'm going to introduce a software layer that allows you to run any application on what looks like a modern data center design, so that you get all of the cost benefits of the Googles and Amazons, but you can do that with traditional enterprise workloads. So that's what motivated Nicira as a company, and that motivated the product NSX, and I'm going to talk a little bit about what that is. So let me try and put a little bit of color on this. So let's say you've got a data center in our, this is kind of my mock data center. You've got a physical network. In the case of NSX, that physical network can be anything with IP reachability, L3 ECMP fabric. Now there are more intelligent and less intelligent fabrics, and NSX will take advantage of them. For example, HP has got a great SDN story. We're great partners, and if there is functionality within the hardware, love to use it. So you have a physical network. Attached to your physical network, of course, you have servers. In a virtualized data center, you have something like, say, ESX. So NSX is very similar to ESX. So the way to think about NSX is, OK, so you have software that's running at the edge of the data center that creates what you can think of as a network hypervisor. Right? So this is just software. It's only running on servers. It doesn't touch the physical hardware at all. And what it exposes is a virtual network. So these look just like physical networks. They support all the services of physical networks, L2 and L3 and L4 through 7 services and all that great stuff. But they have an operational model of a VM. So any application that you deploy, you should be able to snap onto one of those things, and it will work. And it should support the standard operations and management interfaces that your guys are used to using. So it should be able to support standards like SNMP or NetConf or whatever it is. So here's the idea. You deploy a new application. Instead of attaching it to a physical network, which is more expensive and requires more operational overhead, you attach it to a virtual network, which looks exactly the same, but has this beautiful operational model and runs on any type of hardware. Simple? And again, you've never been able to do this in the past at all. Like in the past, to build one of these Gen 3 data centers, you needed to rewrite your application. Now, you can. OK, I just gave the same talk that I gave last year. So what I'm trying to do is I'm trying to catch you back up to kind of where network virtualization came from. And at the time, we had customers, we had some early deployments. We were clearly early on in the innovation cycle, right? It was just early adopters. They were pretty aggressive about deploying. However, and actually, our announcement on Q2 just came a couple of weeks ago. Things have evolved tremendously since then. So I think this is the second public time that I can say these things. I mean, we're already at a $100 million run rate a year business. This is a real business. I know that we've closed over 150 customers. I've been involved in most of those sales cycles. This has been used in production in almost every vertical, whether it's financial, whether it's school, whether it's Fed, whether it's service provider, cloud providers, SaaS providers. And so this is turning into a general technology, a general component that's being used throughout the industry. OK? Which is cool. So now we're actually understanding, we're seeing this deployed, we understand the problems, why people use it, why people buy it. So I want to spend some time talking about why people do buy and deploy this, the benefits they see, and how that use case is evolving, because it's actually evolving into an area that I hadn't expected. OK? Great. OK, so 3 reasons why people buy and deploy network virtualization. So the first, and this is the one that actually, that all of the original use cases was based on, was speed to provision. So that was it. So all of the early users, all of the early customers, the reason that they would adopt this technology is it would reduce the time to provision a network to 0. Right? So the sales cycle would be something like, I'd walk in, I'd be like, hey, listen, OK, so does network provision get in the way between you and doing something, whatever that something is? Is that onboarding a new customer or deploying a new app or deploying a new dev environment? And if the answer was yes, then we could have a conversation. If the answer was no, we couldn't. Right? So early customers were, for example, customers like eBay that wanted to deploy new applications quickly or more new development environments quickly. There were large cloud providers like Rackspace. There are telcos like AT&T or NTT who wanted to onboard customers more quickly. So all of the early use cases were around that. But when it comes to speed, this is kind of an ancillary benefit, right? You're basically saying, I'm just going to do what you do, but faster, and hopefully then your business will move faster. So the second reason people started to look at it was economics, which actually early on you couldn't do. So it turns out when it comes to early technologies, it's very difficult to sell on cost. And the reason is as follows. If I walk in, I say, OK, Mr. Customer, I'm going to save you $50 million on your data center. That would have funded Nicira, right? That's a ton of money. They'd be like, that's great, I want to save $50 million, but I have no idea how to evaluate the risk of talking to you. I mean, you look like a kid. I mean, you've got gray hair, but you look like a kid. I don't have any relationship with you at all. Like, I don't know if your code works. I mean, I saw your office. There's probably 12 other kids in there, right? So I'm coming with something that'll save you $50 million, but there's no way to actually evaluate the risk of early technology. There's no real deployments. There's no real understanding of these things. And so early on, even though we tried to position things around cost, it just didn't work. However, as we've seen the acceleration of the sales cycle, that's changed, right? I mean, now we actually have ROI examples that actually have been in production that came out of real deployments, and people understand the implications of these things. And so there's two areas where people view the economic savings broadly, CapEx and OpEx. CapEx, I've never seen actually someone purchasing this technology on CapEx ever, just because I don't think that the network is a significant portion of data center spend, right? It's like some 10%. But when it comes to OpEx, you can reduce a tremendous amount. And actually, when you look at L4 through 7 services, you can save a lot of money as well. I'll talk about that a little bit later. But the surprise to me is that now, I would say over 50% of our sales are actually around security, which I really hadn't anticipated. And I knew there were security advantages, but it's really driving. And in fact, I think that this is the chasm crossing use case, which is, it's kind of difficult to convince people around speed and around economics to do these things, because you're kind of making these intuitive arguments. But things like security, it's actually pretty easy to have the discussion. And so when it comes to like enabling a sales force and people adopting this stuff, this really seems to be the broad use case. And so I want to give you guys a very, very strong understanding of what the security problem is and how things like this address it. So I'm going to spend pretty much the rest of the talk just focusing on security, because right now it is the main driver, certainly for network virtualization. Okay, clear? So I just want to just very quickly. So I came up here and I said, network virtualization, it basically tries to get you the efficiencies and economics of a Google-style data center for IT, at least when it goes to the network. And then I'm focusing on what the use case has been. We thought that one was a primary use case originally, but it really has evolved down to 3, and now I want to focus on this a bit. Okay, for those of you guys that heard me last year, you know this, but I want to say it again. So I actually come from a security background. So my first job out of college was doing computational physics. I worked on nuclear weapons simulation in the national labs. 9/11 hit, 2001, and then there was kind of a shift in the alignment of the priority of the United States away from kind of this kind of Cold War relic to kind of more intelligence stuff. So I went from computational physics into the intelligence agencies, and I did security. And so I did that for 3 years. I did this kind of under the cloak of secrecy. It was super cool for a young kid. I had a good time. But then I went, back, did my PhD, and I've been focusing on networking, did the work around SDN and network virtualization. And for the last year, I've gotten back to security. And the most interesting thing to me is it's like almost nothing has changed from when I did security 7 years ago. So I want to describe this. So if you look at broad industry trends, and this is so shocking to me, the rate of growth, the first derivative, the rate of growth of security spend outpaces that of IT spend. So we're increasing our spend on security more than we increase our spend on IT, which, okay, that isn't super surprising. But if you look at kind of similar trends, the only thing that seems to be growing faster than the amount we spend on security is the amount we're losing on security breaches. So like if you take like the Windows slider bar and you slide it out to the future, that means like all of our time and all of our money is going to be spent on security breaches if we don't rein in the problem. And so you stand back, you say, listen, we're a mature industry. Let's be honest. We like to talk about being innovators and this and that, and that's all true. We're a pretty mature industry. We've got smart people. We've got real sales channels. We've got real technologies. We've got real innovation centers. We've got a lot of money, tons of startups. Like, why are we having this enormous problem in security? It's not an issue of intelligence. It's not an issue of spend. So why is it? So I'm going to argue that's actually fundamentally an architectural issue. I think it's a fundamental technical issue. I'm a technical guy. I like technology. I'm going to argue it's a fundamental technical issue. But before I do that, I actually want to give you guys an appreciation for a modern attack. So myself and a guy named Tom Korn, who's the chief strategy officer for RSA, looked at a number of attacks, like modern attacks, big companies, and we put together a canonical kill chain. I want to step through it with you guys so you kind of understand how people break in today, and then we'll talk about how we can address this with technology. Okay, so a modern attack. So in a modern attack, it's normally targeted because you're going after high-value things, right? So very often, first step is human reconnaissance. Thank you, Facebook. Thank you, LinkedIn. It makes this much easier for me. I just had my birthday recently. I wanted to let you guys know that my sister sent me a birthday card on my birthday. She sent me a birthday card in email on my birthday. She actually alluded to stuff that I'd done recently, and it was a phishing attack. And this almost certainly came from Facebook, the information that was pulled from it. And it had, of course, like a little piece of code for me to run if I wanted to run it that was attached to it. Now, I thought it was very strange that my sister was sending me something from Romania, but anyways, I didn't open it. But the point is if I want to reverse engineer your organization, I have every tool that I need from behind a computer in my apartment in San Francisco, right? Once you kind of understand the organization and who's there and what's weak and what's not weak, and by the way, you always want to talk to somebody that's less skilled than a primary target, right? I will go after the executive assistant, I will go after a director, I'll go after a contractor. Then you determine your attack vector. I mean, if you're a nation state actor, you build your own. If you're not, I mean, you can have products like Zeus, which will go ahead and create you an exploit, their warranty. They'll provide you 24-hour support to actually create an exploit to get in. And then you determine your primary attack. Okay, and again, this is taken from real attacks, real data. All right, then you go ahead and you compromise your entry point. And again, coming from this world, let me tell you, you can always get code on a server somehow. Whether you're buying someone off, you're paying the guy in the black mask to kind of break through the window and kind of shimmy under the table, install code, doing some remote exploit, supply chain attacks. In fact, in the case of the RSA attack, there's a supply chain attack where the attacker compromised one of the guest workers before the contractor was able to walk into the data center. Somehow you're going to get code on one of those servers. And it's actually not that hard. Once you do that, once an attacker does that, you install command and control. So you've got an interactive session with the attacker, and you put two strains of viruses, or malware, strain A and strain B. Strain A wakes up, strain B is asleep. All right. So now, strain A is awake, will escalate privileges if needed. It depends on the type of attack, and it will start to understand what's going on in the network. So this is things like look at connectivity, look at users, look at use patterns, look at logs, look at logging infrastructure. So it's providing it's gathering a bunch of information, it's providing this information back to the attacker. So the attacker is gaining knowledge the entire time this information is being collected locally. And as possible, strain A, which is awake, is also going to try and laterally move about. Do another compromise. Again, this intelligence doesn't have to exist in the malware when it was first planted, right? This is an interactive session with an attacker. So the attacker's like, oh, well, maybe we can try this exploit on this thing, or maybe we can try to do some redirection attack on this thing. So he's interacting with this piece of malware. The malware is moving around. And at some point, maybe somebody's going to identify strain A and clean it up. In the case of one of these attacks, it was identified. It was cleaned up. Strain B wakes up. It now knows what was tripped off, connects back to the attacker. The human being attacker, the attacker talks to strain B, plants strain C, and we start all over again. So what's happening? We've got an interactive attacker that's working with this. We've got multiple strains that are going on. You've got A, you've got B, then you'll have maybe C and D. But you go over time, and each time you're learning more about it, and you're moving around. So at some point, I mean, the purpose of a targeted attack is to get something of value. Otherwise, I mean, this is no longer, kids doing it for glory, right? And so the thing of value is almost always data, whether it's credit card information or privacy information or state secrets or whatever it is. And so at some point, the malware is going to have to try and break in. And this actually takes a long time. Often this will take months, whether it's using brute force attacks or it's going to use some low-level OS bug. I mean, often it'll try and get at, like if it's encrypted data, it'll actually try and get at the key, which is actually not difficult to do. At some point, you're going to break into the store. Then the malware will take the information, it'll parcel it up. Often it'll steg it into things like JPEG, so like images posted on Facebook or whatever, and it'll exfiltrate the information out, low and slow, again, over months. So virus goes in, or the malware goes in, it breaks in, it gets the data, it chops it into little packets, it goes ahead and uses basic steganography to put it in data, it exfiltrates it out, and once it's done, it cleans up. And normally, in most cases, the only time a company knows it was attacked is when the FBI told them they were attacked. Honestly. Okay, so let's take a step back. Okay. So this is kind of the kill chain. Remember, this is targeted. It's highly interactive. And it's incredibly stealthy. This is a very low and slow. And again, this does a pretty good job of summarizing many of the high-profile attacks that you guys read about in the news. So it's interesting, and I've heard other talkers talk about this today. I'm sure you guys hear about this all the time, but it is worth pointing out again that pretty much all of our security technology today is focused here, which is actually kind of the easiest part, right? I mean, there are stories of intelligence agencies that when they break into accounts, it's just an economic exercise. They're like, listen, I know how much it costs to pay off some guy in random country X or random company X, and it's probably less than $50K to get him to install some software. So here is where the majority of our security is, and this, we have almost no protections again. And so I want to talk about why that is, because it's not because we're dumb, and it's not because we don't understand the problems. There's actually a very real technical reason why we spend all of our money on the perimeter trying to keep people out. Okay, so I'm going to go there. Okay, you guys have heard this in the two talks before me. You guys have heard it many times before. Security is perimeter-centric, which means that we spend 80% of our security dollars on the perimeter, keeping people out of the data center. And if I, as the attacker, am able to break in, then I have unfettered access to the data center where all your data is and all your code is. Why is that? The reason is the problem of securing the perimeter is actually pretty trivial. So for any data center, say the biggest data center you have, how much data do you actually have to handle to secure the perimeter? 100 gigs, maybe. If you're really huge, probably 10 gigs in and out of the data center. You can do that with a single x86 box and 2 for HA pair. So every time you buy an appliance, whether it's a firewall, a next generation firewall IDS, or an IPS that handles 70 gigs, that's great. You've basically bought something that will protect the perimeter of your data center. Okay, now let's look at the problem. So if you want to protect traffic going in and out here, you can buy one x86 box server that's a $5,000 box that has enough capacity for almost any data center. You just need to write software to it, right? So what is the problem of actually protecting within the data center? Well, one top-of-rack switch is what? 48 ports by 10 gigs, that's half a terabit. That would require 5 appliances per every top-of-rack switch. You probably have thousands of them. So if you actually wanted to provide controls in here, you would have to have 5 appliances per top-of-rack switch. You would have to have hundreds of these things, 5 times as many top-of-rack switches as you have, if you actually wanted to do this at speed. Not only would you have to do that, you'd have to have someone running around managing all the rules between these and keeping these rules consistent and these rules updated. It's totally it's ludicrous to begin with, but it clearly is capitally intensive. It's operationally infeasible. You just can't do it. So the technical problem, this is a technical issue, the technical problem of solving security within the data center. Right now, we don't have, or we haven't traditionally had, the technologies, because what we do is we deploy boxes at the edge, and we don't know how to build services that will scale to many terabits. That's the traditional problem. And by the way, if we take technology and we put it in the application, that's fantastic, except for the application is an attack surface, right? Meaning, if I break in, I'm probably breaking into the application, the code changes all the time, it's not written for security sensitive, and then I just go ahead and I turn off whatever security controls you put in there. So application level security does not have the type of isolation that you really want. So that doesn't solve the problem, which is why we put stuff in the infrastructure to begin with, and we have no idea how to do it in a way that we have ubiquitous coverage. Okay, so it turns out that network virtualization just natively solves this problem. Actually, so network virtualization natively solves this problem because it takes any arbitrary service and it distributes it along the edge. It's actually part of the technical thing you've got to do when you build a network virtualization solution. So I can, for example, take a firewall and say, okay, instead of having a firewall that's 70 gigabits on the perimeter, I'm going to build a 10 terabit firewall that goes across the entire data center, and then a little bit of that firewall runs on every one of these servers. And part of the technology of network virtualization is ensuring this is consistent and ensuring you have a global abstraction. So one of the core uses and adoptions of network virtualization is simply microsegmentation. It basically says this: for every application or user or whatever I want, I'm going to give it its own little isolated domain. And in that isolated domain, I'm going to give it its own security services, whether it's a full firewall or it's a load balancer or IDS or whatever it is. And if that application gets attacked, the attack is limited to that security domain, that virtual network. So I just want to contrast these two things. If I spin up a VM in a traditional data center, and it gets attacked like I talked before, and I scan around, I can attack the physical infrastructure, I can attack AD or LDAP or DNS or DHCP or any other physical server or whatever else I want, because it's all this big shared infrastructure. If I spin up a VM in a virtual network, and that gets attacked, and it scans, it can only see anything else on that virtual network, not the physical infrastructure. Maybe there's some shared services, maybe not. Often these are actually copied for a virtual network. It can have its own firewall. Even if I compromise the firewall, it's still limited to my virtual network. So now I've reduced the attack aperture from everything to actually a fairly small bit. And this is to do what's called enforcing the principle of least privilege. The principle of least privilege just basically says, if I have an application, it should only have access to the stuff it needs to get something done, right? So now you have an erector set of these components that you can use to make sure that anytime you spin up an application, it only has access to exactly what it needs to get done. And this is the driving use case in the financials. This is the driving use case in the Fed space. This is the driving use case in the airline industry. This is the driving use case in many of the enterprise because, A, there's been a litany of attacks lately that have been very highly publicized, and it's just a better way to do security. So I want to actually step very quickly through kind of what this looks like from a kind of a packet perspective. So, today in a data center, you'll have a firewall on the edge, which means if somebody compromises a VM, they'll have access to all of this stuff without any security controls. So the idea is okay, can we instead, well, here, I'm going to send a packet. So the packet's going to kind of go. So a firewall will drop it if it goes out, but if it stays within here, there's no security controls. And just so you know, as we consolidate more workloads into the data center, fewer and fewer traffic actually goes out. In a standard data center, about 80% of the traffic never actually crosses the perimeter anyways. So like 80% of your dollars are on like 20% of the traffic, which that also makes no sense. So instead, the idea now is say, okay, what I can do is instead of having like one firewall that sits here at 70 gigabits per second, I'm going to do it as I'm going to take this security policy and I'm going to actually push it to every one of the hypervisors. So I've got a global abstraction of a firewall. Now, anytime I send traffic, I do local enforcement on the server. All right, so you've taken now the attack aperture of an entire data center and all the trusted computing base there, which is tens of millions of lines of code of shared services, and I've reduced it to basically what exactly you need to communicate, and that's it, and no more. And of course, because this is part of a virtualization layer, you actually also have the operational model of virtualization. If things come and go and move and grow and shrink and whatever else they do, the security policy remains totally consistent without requiring human beings to do that. Which, by the way, it's very difficult to do sane security policy in virtualized environments because VMs move and security policy doesn't, traditionally. OK, so I just wanted to give you guys an intuition of how sophisticated modern attacks are, and I wanted to make an argument that this is actually a technical problem. Like, we actually, as computer scientists and networking people, have not known how to address this. We actually haven't. I don't know how to do a fully stateful distributed firewall traditionally that spans an entire data center, so I can't do the controls. So I actually want to start pushing this a little bit further. So I'm going to start talking a little bit in the future of how this is going to evolve going forward. OK, but I need to set it up a little bit. OK, so what's the Goldilocks zone? So the Goldilocks zone is actually a term that planetary scientists came up with in the 1970s to talk about like the perfect region in the solar system where a planet can be to sustain life. So it's not too hot, it's not too cold, it's in this Goldilocks zone. OK, so I believe that actually, if you have a virtualized infrastructure and you have a hypervisor, you actually are in a Goldilocks zone for implementing security. So I'm going to talk about what that means. OK, so typically when we do security, and I mentioned this a little bit before, we do this trade-off between context and between isolation. And what do I mean by that? So if we put security controls in like an application, for example, we have a lot of context. So if I take some security service, whether it's access control or authentication, whatever it is, and I implement that within the application, I know a lot of stuff. I know users, I know data, I know what information is being processed, because it's in software and it's at the edge and you have that type of information. So that's awesome, right? You want to have security that's really knowledgeable about what it's securing. But the problem is, like I mentioned before, it's like putting security controls there is like taking like the on-off switch to an alarm system and putting it on the outside of a house, right? That is the attack surface. That's what you attack, generally, is the application or the user space code. It evolves too quickly to secure, I mean, it evolves all the time. Generally, it's not written by people that are security conscious. And you're in the same trust domain. And so application level security has been a very difficult thing to pull off, because once it's undermined, it's undermined. So if you put a security control there, OK, not so good. On the other hand, if you put a security control in the infrastructure, you got the exact opposite problem. So if I take my security control, instead of putting it in the application, I put it in the infrastructure, like it's an ACL on a top-of-rack switch, or it's a firewall on a separate appliance, you actually have pretty good isolation. Meaning, if I'm able to compromise the application, I probably can't turn off the ACL or compromise that second box. I mean, that's good isolation. But the problem is you've lost all of your information. Like, you have no context. Like, networking is a discipline of guesswork. Like, routers don't know users. They don't know applications, really. They often don't even know end hosts. They know nothing. I mean, we use like ports and MACs and all these like low-level things, and we know nothing about that. So it's very difficult to implement sane security policies. And it's kind of funny. I worked in an intelligence agency. We had a very complicated network. We tried to enforce a good security policy. It was impossible to answer the question, can A talk to B? It was impossible. I mean, it's just like you've got all this low-level state distributed all over places and things moving around, and it's very, very difficult because we don't have any real handles to do this stuff. And so security has always been kind of this, in data centers and IT, has always been this trade-off between, OK, I've got all this great context, like I know users and applications, and I'm there, but I have no isolation, and I've got this no context. I have no idea what's going on at all, but I've got great isolation. So the work that we've been doing is trying to figure out how you can bridge these two things together in the context of network virtualization. So if I bring you along kind of like the narrative that I stood up here to start out with, I'm saying, OK, network virtualization, lots of people are using it. The primary use case is this microsegmentation, which means I can actually have much more secure environments. Now what I'm saying is, not only can I do that, not only can I provide microsegmentation, I can actually provide you a meaningful policy over meaningful things. So I can both give you the ability to do policy over like users and applications and whatever, but provide you a level of isolation that's meaningful. And the only reason that you can do this is because you basically have a piece of software that's running at the edge that's also infrastructure. The only reason you can do this is if you implement security controls like in a hypervisor, or it doesn't actually have to be a hypervisor, any like security layer, horizontal security, if you implement your security control there in a way that's isolated, it can't be turned off, but it's co-resident with the application in RAM. Like you're there in RAM. So you can look at things. So from like a hypervisor, I can look and see what applications are running by looking at the file. I can see what users are on there. I know everything the operating system knows. I know all of this information, and I can use that to enforce security policies. I'm not guessing. I'm not looking at IP addresses or MACs from within the network and just guessing. And so the goal is, and this is why I call this the Goldilocks zone. I think it's kind of, if we're able to do this, and this is actually future stuff. I mean, we have it working, and there is like a lot of momentum. There's a lot of big customers that are starting to work with us on this. If this turns out to be a viable direction, again, technologist, I'm not sure it will be. If it turns out to be a viable direction, it'll finally solve this gap that we've had in security for a long time. So I want to go ahead and end and walk through the impact and the implication of this, because it might not be obvious. It seems like this very simple thing, which is, OK, well, you've got the ability to have context and isolation. What does that mean to me? Well, I think this actually cuts across most verticals in security. I think it'll actually change most verticals, significantly change. And so I actually want to walk through 3 of them. These are actually active partnerships that we have. These are things that are actually being implemented. So let me talk about vulnerability management really quick. So what is vulnerability management? Normally, vulnerability management is you have some appliance that sits on the network, and it scans things, and it uses really simple techniques like banner fingerprinting to determine if something's vulnerable. That's typically what vulnerability management is. And then if you determine something that's vulnerable, because like the response that it got was, had a string that was vulnerable, then you'd issue a trouble ticket, and someone would go ahead and remediate it. So there's many problems to this approach. First one, like remotely scanning something is a horrible way to determine if something's vulnerable, and it's trivial to spoof, right? If I'm malware and I compromise something, I'm gonna, if I get queried, I'm just gonna return the right string, right? Second, even if you determine if something is vulnerable, there's not very much that you can do unless you have a human being try to remediate it. So like now you've got like an attack window of between the time something's being attacked in the time a human being is able to remediate that. Okay, so now if you use kind of a Goldilocks zone approach to this, which we have now working, so imagine instead of having some remote box scanning an entire data center remotely using remote fingerprinting, you actually have the logic sitting in there on the server, have direct access to the files. So you check some of the files, you know the running processes, you can know the processes in memory if you want. So I can tell you exactly whether this is a vulnerable application. It doesn't even have to be like a file check. It doesn't have to be what's on disk. I can actually look what's like running in memory. Right? It'd be very, very difficult for something to subvert a system like this. Not only that, because I'm there already on the box, if I determine that something's vulnerable, I can immediately remediate it. So for example, I could say, you know, instead of being able to access the network, I'm just going to make sure that you're immediately quarantined. Right? So anytime something that's vulnerable that's detected, instead of issuing a trouble ticket, it'll just immediately quarantine it so it only can connect to a remediation server. So I think this has actually fundamentally changed like the nature of vulnerability management. Same thing for like, say, malware protection or network protection. When I talk about context, I'm not just talking about users or I'm not just talking about applications. You can actually determine the end state of a machine by like saying, is it infected with something? So let's say that you have, I don't know, Trend Micro running within this, and it's scanning files in real time, and it determines that a VM actually has a virus on it. By the way, it can do this scanning from a totally different address domain, so it can't be turned off, right? So it's looking, it finds something is infected. So again, because you can have this context, you can actually use this as part of your firewall policies. So my firewall policy, instead of saying, oh, okay, if this is Martin, do or do not let him do something, I can basically say, you know, if this has a virus on it because Trend Micro said it, then only give it access to these types of servers. So now my security policy is now built around kind of deeper understanding of what's going on the edge, something, again, we've never been able to do ever. And the same thing goes to network protection, which is kind of a follow-on to the malware protection, which basically says any policy for any access to the network can actually be driven over meaningful things, whether it's users or it's applications or it's security policy. And it can be remediated over things. So what you're going to see is certainly from us over the next year is a continued focus on this. I mean, we actually now have deployments that are coming out. We have a lot of partners that are working on this. And like what I want to do, if I get invited to talk next year, I want to come out and say, listen, here's a security policy. Actually, by the way, my entire PhD was trying to implement a sane security policy in networking, which I can prove is impossible. So it took me 4 years. So if I come back in a year, I want to be able to say, listen, we've got this working system, this set of partners. Here's the security policy that we've implemented today, and it's running throughout the entire data center. And it's done in a way that we've never been able to do ever. And I think we're so close to doing it. I think this is the last piece to like fully automated policy-based IT. I really do. I think this is the last piece, and hopefully it'll slot in time. So that's going to go ahead, and I'm running out of time here, so I'm going to go ahead and conclude, but I just want to very quickly summarize. So network virtualization is cool. It's being adopted at scale, and now we have a business that's well past the knee of the curve. We actually have a lot of production experience, which is great. The driving use case is security, which we knew would be something that was interesting. We didn't know how interesting it would be. And we're actually evolving the technology now, not just to provide global security policy, but to imbue that with context that's actually meaningful. So anyways, I appreciate your time. Thank you so much.